Here, my name is Mustapha Ishak. I'm a professor at the University of Texas at Dallas. I have been also for 4 years, over than 4 years, as the convener, co-chair of the cosmological parameter estimation working group in DESI. So I will report to you today some results from DESI, but also some pluses that I have been working with a collaborator, Leonel Medina, and I will report to you those ones with a nice objective in mind that at the end we will converge to some concluding observations. Again, and thanks for the invitation. It's a pleasure to be here. It's a different audience. I'm learning new stuff. Very well. And first of all, I would like to thank our sponsors, in particular DOE and NSF in these particularly hard times, and also thanking our 72 institutions, 900 members of DESI collaborations, working all as a team to put this result and make them possible. All right, so DESI was an experiment that was designed and thought from the very first in order to try to measure the equation of state of dark energy. And it measured positions and redshifts to millions of galaxies and millions of quasars. It did so in the first year. It did 6 million galaxies and quasars. And then after, in the third year, it did 15 million galaxies and quasars. And now working on the last objective, which is the 5-year data, to collect about over 40 million galaxies. If you're interested in the formalism, the procedures, all the work the details that we have done, you can look into these papers here. But I'm really delighted to tell you that today, in this moment, in this week, we are measuring the last tile of the DESI survey of 5 years. It's happening this week. And with that, we will conclude about 47 million galaxies and quasars. So it's a 5-year program, and it happened that we are closing it exactly these days. Okay, good. Before I proceed, and again, I have one slide for definition of dark energy, why we care about the equation of state. I got some questions in the last day or two I was around here. And so I put this slide here. Dark energy comes into the universe, can be modeled as a fluid, as a perfect fluid with an energy density and a pressure. And then it is important. It represents 70% of the dynamics in the universe, be it energy, dynamical effect, gravitational effect, but it is substantial, 70%. We characterize it in general using a variable called the equation of state of dark energy. That is the ratio of its pressure and over its density times energy density times c squared. Why do we care about this W? Is because, first of all, if you take the Einstein field equations and you take the Friedman equations and you put into them a dark fluid that has an equation of state that is smaller than -1/3, it actually makes the expansion accelerate here, a positive acceleration. That is one. Two is different candidates of dark energy may have different values of this W, the equation of state of dark energy. So there is a big interest into measuring these different Ws in order to distinguish between the different candidates of dark energy. And that's what DESI and other experiment has taken as a chief objective. How DESI does that? So again, it measures positions and redshift of millions of galaxies and quasars. It starts at the lowest redshifts with the bright galaxies, 13.5 million of them. Then it moves on to the LRGs, and about 8 million of them, 16 million of the ELGs, and then it goes to deeper in redshift space towards quasars. It measures 3 million of quasars that are used as tracers themselves for the correlation functions, but they also, in the background, they also emit and they also produce the light for the Lyman alpha forests that are used. And you see, when we did this slide, we were aiming for 40 millions, and it's very good that we did more than that in this moment. Good. So what is the probe that is used by DESI? So very early in the universe was a plasma, and then so there is photons and baryons, and so in that plasma there is gravity tries to bring things down, to collapse the matter, to collapse the fluid, while the pressure of photon pushes back. So there were these kind of oscillations between the two. There was this oscillation, and then from the time of the Big Bang, and then the universe is expanding, and at some time there is not enough energy, so there is a decoupling. There is, after recombination, there is a decoupling between the photons and the baryonic matter, and in that decoupling, so the baryons were free, and then the photons were free. The photons, you see that in the CMB. You see the peak, the big peak in the CMB, and then in the baryons, there is this characteristic scale that you see. So the matter is focused, is concentrated into these shells of matter that you observe. So this, at the time where there was this decoupling or the dragging effect, the baryons were a little bit lazy, they drag themselves a little bit. You have this characteristic scale of 100 megaparsec. It's the transverse sound crossing horizon R sub D here. And that one gives a standard ruler in the universe. So we can use it as a standard ruler. And that's what DESI does. It uses that standard ruler into two directions. One direction is the direction along the line of sight, this guy here, and the other one is in the transverse to the line of sight. So you have two ways to do it. The first one here, let's say, this one, so this angle is sustained by the sound crossing horizon RD, and this theta, of course, is related to also this distance, the transverse distance, so the co-moving angular diameter distance. So by finding this theta BAO, this separation, characteristic separations, and knowing RD, we can get D sub M here. We can get the co-moving angular diameter distance. And then also, by knowing this characteristic also separation in the redshift space along the line of sight, we can also from it determine directly determine H of Z, the Hubble function. And in fact, with that, we can determine precisely, with some precision, the expansion history of the universe. In fact, DESI goes after dm over RD, dH over RD, dV over RD. And all of them, you see dm over dm here, it depends on this hz over h naught, same for dh, same for dv. And in fact, this function h of z depends on omega matter, omega curvature, omega of dark energy, and also the equation of state of dark energy parameters, W naught and W1, or simply you can use it as a function epsilon here. Now, as we said, this is one really cool thing about DESI is that it has these different probes. So you have the BGS, LRGs, another group of LRGs, LRG3 plus ELG, ELG2, quasars, Lyman alpha. So you see there are different redshifts. And being a different redshift and used, they give you constraints here about on omega m and H naught RD. These constraints, they don't go all in the same direction of degeneracy. The direction of degeneracy changes with the redshift. So these probes actually then they are complementary. They are complementary, they add up, and they are compatible, but they add up. So at the end of the day, they give us this very small here constraint on omega m and H naught RD. In fact, it gives us, so just DESI by itself, just the BAO, it gives us a 3% measurement of omega m. It also gives us a less than 1% measurement of HRD. So now we start doing some cosmology with it. We're going to start to look into so we are looking into the lambda CDM model. And then we'll move on to the dark energy models. But for now, let's have a look at the dark energy models. The lambda CDM to start with. So in the lambda CDM, first observation. First observation is, if we look at within the lambda CDM, the flat, we are setting omega k to 0. So we're looking at the flat cosmology. You see that in blue here, this was the first year of data from DESI. So this is the third year of DESI. And then in dashed lines here, it's the first year of DESI data. So we gained into precision. But you notice now we start seeing within the lambda CDM model, we start seeing some tension here rising up here between, this is what the CMB, what Planck and measures here, and this is what DESI measures. So we start seeing some small discrepancies at the level of 2.3 sigma. We dig a little bit farther. We can use BBN. We can use the measurement from BBN. And then when we use the measurement from BBN, if you see here, we can break the degeneracy. We can break the degeneracy between H naught and RD. We can have a bounds on H naught, constraint on H naught. And if you look at first of all, the plot here, if the blue here, the combined DESI data, it is far away from the shoes measurement, the local shoes measurement, the local measurement of H naught. And this is, of course, the Hubble tension that we have been talking about for 100 years now. And you see that this is the first point where I would like to pause for a few seconds. If we look at this result here, this is a less than 1% measurement on H naught. In 4.5 tension with the shoes local experiment. So this is no CMB. Let's forget about the CMB. So there seems to be a significant tension between the local measurement of H naught and the BAO, the DESI. That's point one. We did this in the first year, in 2024. We combined DESI and the CMB to look how well we can constrain omega k curvature, and we did. And we got this tight bound on omega k. It seems like curvature seems to be very close to or very small and supporting spatial flatness. And now I move on to probably one of the main results of the talk today, but we have then after that, I have some new stuff for you. And this result is as follows. So I was talking in the last 2 days, I was talking with a few people here, and I figured out some of you know some of this stuff very well. So sorry if there is a repeat. Some actually didn't know about that, in fact, what is giving what constraints. So that's why I'm going to give this as a little story about this. But those who saw some of this, I have a very nice slides and punch for you afterwards, so don't worry. There is something for everyone. So here, why I like to say this story, and it's the night of December 12th, 2023. So this was a Tuesday. So why I remember it, because that day we did the unblinding. We were at the DESI meeting, okay? DESI meeting, it was in Hawaii. It was a beautiful weather, but honestly, we didn't see any of that. That Tuesday was so important because we were unblinding the data and see what it's going to tell us. So we unblinded the data that morning. We took the unblinded data. We ran to we put that into our Monte MCMC chains, into our pipelines, because we were working for years with just the mock catalogs, with just the simulated catalogs. We were working then after with the blinded data, so blinded data. So we were really so eager to see what the real data is telling us. And that Tuesday, December 12th, it happened. We put that into our pipelines, and it were running. So from the morning, and we stayed until, I toughed it up until 1 a.m. I was exhausted, went to sleep. We had some other friends who were online staying. So I woke up at 6 a.m. and I checked. The chains started converging, and we ran. I plotted myself. My other colleagues also plotted them. I plotted something like this orange curve here. And the thing that struck me the first is it did not touch with this dot here, with this cross here. This is the vertical line for -1, W0 -1. This is the horizontal line for WA equal to 0. And surprisingly, it did not touch. And the chains converged and converged, and it didn't touch. So already, I think it was like in a 2.6 sigma that the first year in tension with the lambda CDM, with the cosmological constant. So we figured out that something funny was ongoing. And the story started to become interesting when we plotted these things here as well, okay? DESI plus the CMB, sorry, DESI plus the supernovae. So you see that a kind of a pattern or something supporting the same finding here. You see that if we combine with DES, with DESI, or we combine union with DESI, they are also away from this point of a cosmological constant. So only the Pantheon plus was keeping lambda CDM alive there. Okay, so okay, and then in fact this trend was, to me personally, was very important from the start. And then what we did, of course, the next thing to do is to put them all the three together. And we did that. And it's funny, some of you heard me already saying this, but it's true that at the beginning, now it's okay. We are used to this one. But at these times, I remember when I did these plots, and when me and other colleagues, so when we push on the Jupyter notebook, and I remember we take a deep breath, because it is true that it's kind of, you don't know what the universe is about to tell you. And that's real. It's a cool feeling. And again, so the universe in this case, when we combine these three, the universe did not disappoint, okay, at that time. So you see that it's only get worse. the separation, the exclusion of the lambda CDM only got more serious and away from a cosmological constant. So these contour plots, all of them exclude the cosmological constant with different level of significance. We started in year one, so it was 2.5 sigma, 3.5 sigma, 3.9 sigma. We did some other DIC and other things to check what's if this isn't, it's all gave us the DIC and all this gives us the same consistent story. All right, so I think we were very prudent. We presented this at the APS meeting in 2024. And if you see it, you will see we have to be very prudent with this. But if this is to stand, it's a very important result. And we were very careful about it, cautious about it. And however, we did celebrate a little bit. So we did, in fact, it happened very well. You see this picture here. This is at the announcement in Sacramento, 2024, the 4th of April. So it was really cool. But then another cool event. So we had the DESI meeting in Marseille, in Marseille, and we met. If you are close enough, you will see they got for us tons of really some wonderful French pastry to celebrate. So it was a very nice meeting to get all together and to reflect on our results. Now, a year later, we had because we did year one, it took a little bit time, and then we did year three of the data in 2025. The evidence in 2025 went up. The evidence, the 2.6 sigma that I showed you, got to 3.1 sigma without any of the supernovae, So we got to 3.1 just from the CMB and DESI. If you add to it the three different supernovae, then we get 2.8, we get 3.8, we get 4.2. And these are the curves that are here. All right. Exciting results. But now, again, this is in 2025. Now in 2026, so we have the supernovae people, they recalibrated their supernovae. Okay, I hope that the last time they will do that. Okay, we will see. So they recalibrated the supernovae, but nevertheless, I think the result with DESI and CMB stands. So now the current result, and I will show you a little bit more in some slides. I will show you. So we got the result 3.20 sigma, 3.2 sigma, 3.33 sigma, 3.30 sigma here. This is for, so you look at this one here, you will notice two things. You notice the first one is that, yes, the significance went down, but also what you notice, the message is consistent. Now the message is robust, is more consistent. So what we added here for the supernovae, we added the recalibrated union 3. It became union 3.1. You will see more result. We got also, instead of DES year 5 supernova, we put the Dovicki version of the calibration. And also for the Pantheon Plus, we got the recalibrated Pantheon Plus. So this one went up, and these two, they went down. And so there is some now more agreement between them. Yes?
Can you explain exactly how this recalibration procedure works? What are they doing when they recalibrate it?
It's a good question. I'm not a supernova person, but what I can tell you is this. What they did before, for example, in Union 3 and in Pantheon Plus. So they got kind of some way of calibrating the small redshift and the high redshift in slightly different way. So then they come up with some likelihood methods to calibrate them all in the same homogeneous way. That is one of the things. And modulo, they also found the two bugs in their codes. So they fixed them and they got this. All right, the story continues. Now I move on to what Cora said more. Okay, so some results from DESI and more. So this will include some of DESI, but now pushing it a little bit further. Pushing it a little bit further is, so one thing that I wanted to put more weight into that thing that got me very excited from day one. I wanted to put more weights into it and see and put that in evidence. So I said, okay, there has been 2 years of debates, discussions about the contribution of the supernovae to this. All right. Let's see what we do without the supernovae at all. Okay, let's set aside the supernovae and see what we get. And in fact, to do that, I also I brought into play, I don't know if you can see it there from the back, the DES, the Dark Energy Survey, year 6 BAO. So DESI has its own BAO, but also the Dark Energy Survey, 6-year data, they do have their BAO data. So I brought that up and I put it into my into the pipeline. I also added, and it has to be done very carefully because there is some part of the sky that is in overlap between DESI and DES. And that's why you see the word here, no overlap. And so when I did, there is the TAC, the Texas, yes.
Okay, so 2 questions. How much of the data set is in the overlap? And for that overlap, do you take the DESI data or the DES data?
For the overlap, I take the DESI. Yeah.
And then what percentage of the, like, is it overwhelmed by the essentially how much of the DES data are you throwing away?
It's a good question. I don't know the answer, or I don't know the precise answer. I think if you want to know exactly, Mena Fernandez did that kind of cleaning between the two. He published a paper by himself just for that, and he will give you the detail. But all I can tell you is from the 14,000 square degrees of the, it's small. It's not huge, it's small. In fact, I tell you why. Even the DES paper, when they published their paper, they actually did not do this cleaning. And they say it must be small. And you will see the effect is like sometimes 0.1 or 0.2 for the significance, which tell you that it's not significant, that overlap. All right, good question. And now here is another thing you can do is, so you see that this exclusion of lambda CDM is regardless of the supernovae. So why I insist on this one, because people will read in the paper, in the archive, they will see, oh, the supernova recalibrated, okay, all the evidence is gone, or whatever it's this general like message. This attests at the opposite. That's not the case. The case for the dynamical dark energy is beyond the supernovae. It says it stands without the supernovae. Moreover, here is what I really found cool as a plot, and I'm going to share it with you. This plot here is the DES year 6 PAO, no DESI, plus the CMB and the CMB lensing. And yet, you see that this stands away from a cosmological constant. No DESI in that. All right, and now I keep going. I will say, I just like to make some jokes. I would say, okay, if you get annoyed one day by the CMB and say, okay, I don't like the CMB. You wake up one morning, I say, it was the supernova. No, I don't like the CMB. I want to set the CMB to the side for a moment. You can do that too, okay? You can do that too for this purpose here. If you exclude the CMB, you see that the pattern continues, and these 4 plots here, this is the point for a cosmological constant right here. And by the way, I like the CMB, okay, don't get me wrong. So if you set this, you exclude the CMB, this is the latest data. What did I put here? So the DESI DR2 data, the DES year 6 BAO data, no overlap. And then the three, this is the most, this is like history, and this is the state of the art where we stand today. This is plus the revised Pantheon Plus. This is plus the revised Union 3.1, and this is plus the revised DOS Doviki. And you see that yes, the evidence is diminished. The CMB plays an important role in breaking degeneracies, but then you get here again is a 2.22 sigma, 2.17, 2.23 sigma. In other words, I will show you later a landscape, not a string landscape, but a landscape of delta chi-squared for the preference of the dynamical dark energy over lambda CDM. So bottom line, the preference stands, even with no CMB. And the last thing that you want to do, and this is the thing that I did not have last year. We had some interesting workshop last year in Princeton. I already had some versions of these plots, early versions, but this year I'm happy to have also the plots. Oh yes, so what I did here is, actually what I did is, if some of you like numbers, you will have them on my slide. So I have all the numbers there for you to check, including the delta chi-squared, the n sigma, the values of the cosmological parameters in both the W not W LCDM and the lambda CDM. I just put them there. So now I could also say I don't like BAO. I want to put BAO to the side and see what we get, and we did that. Here you will see two messages. One, and this is where you see the results. So you see that the evidence, and we'll see it later. So the evidence is smaller indeed without the BAO. So the BAO is a strong component into this. However, you see that the trend continues. So with smaller significance, 1.77. 1.66, we have here 2.35, 1.98, 2.64. So even if you exclude the BAO, the trend continues. And again, I have the numbers here for those who like numbers. If you have questions later, we can dig into them. Now, if we put all the data together, the three probes together, if we put the three probes together, you see, this is the result I showed you before with 2.85, 3.78, 4.2. Now, here we go. We wanted to change this. Okay, this is what we changed. This is going from here to here. That is when you update the supernovae. Okay, this is here with the Doviki version of the supernovae, the Pantheon revised, and the Union 3.1. So the significance changed to 3.20, 3.33, 3.30, as I showed you earlier. We can push it a little bit more, and I did that too as well. I put the DES year 6 BAO here, I added that. And if you add, it gives you a little bit here. It gives you some, I can't read from there. It gives you, so 3.25, 3.36, 3.35. So it's something that is getting close to 3.4 sigma. And this is if you put them all together. So the message to take here is that, first of all, the evidence is coming from different data sets, and the revised version of the supernova did not do that much. In fact, it made the things more robust, in my opinion. Okay. This one here is my last slide of this type for this kind of things. This is a slide where I said, okay, as a reasonable scientist, as a careful scientist, you can say, okay, if let's put DESI aside. Okay, let's put DESI aside. Let's use the DES 6BAO plus the CMB plus the three other types of supernova, the three compilations of supernova, one at a time, one at a time. And you see the trend is there. You can see the contour. The cosmological constant point is still excluded by the three of them at the 2.05 sigma, 2.48 sigma, 2.45 sigma. So even if we don't put DESI here, okay? Don't tell to Mike Levy, the director of DESI, that I showed you this slide. Anyway, it will be in the revised paper. We have a paper with my collaborator, Leonel Medina. I will put it, I'm going to go back to Dallas after that. Maybe, hopefully by mid next week, I will put this there. Hopefully he will be too busy trying to get us money with DOE, so he will not notice this plot. Yes.
So I have a question about history. If this is the case, why did the discussion of evolving dark energy not come up soon?
It's a good question. It's a good question, and that is the in fact in February, this result here, the BAO6, this result here, this one, and the supernova from the DES and the CMBL, they were there. And if you go and read the paper that appeared on February by the Dark Energy Survey, and our paper appeared on the April 4th, 2024, okay? You look at their plots, and they had something like this. They had something that was away from a cosmological constant. They did have it in the plots, but in the conclusion, they say everything is good with lambda CDM within 2 sigma. Okay.
Within 2 sigma.
They said within 2 sigma. But they did have something like 2.4 sigma or 2.5 sigma. And Cameron was there last year at the meeting we had at Princeton. Josh was there, and they said we saw it, but we wanted it to be more conservative. But I think you should tell what your numbers. That's something important. A lesson, I think, is that you should tell what your data is telling, and then you can interpret it the way you want. You can interpret it like you think is the best way to, but you should not. So they did see something, but they didn't have enough. They did not have like enough confidence to, yeah. Yes.
So CMB, can you tell what data?
Oh yeah, sure. So it's, yeah, so sure. So it's Planck PR3 plus the CMB lensing PR4 from Planck and ACT. That's what is here. No SPT. Yes, ma'am.
But DR3 has this lensing problem, right? This lensing tension.
PR3, you meant, yes.
DR3
Yeah,
From Planck.
yes.
So if you were using DR4 from Planck, that would go weaker.
We did. It is in the paper. We used the ComSpec, okay? In fact, in the result I showed, this result here, and this uses PR4, use ComSpec likelihood. So it doesn't change much. We also use the lollipop, helipop likelihood. So we were very careful. Yeah.
And it should, if this is DR3, then using DR4 will make it slightly weaker.
This is DR4.
Sorry,
Sorry, we're talking about PR4, right? Because PR4, yeah, for lensing. This is ComSpec, PR4. ComSpec is a likelihood for PR4.
Okay, you say the PR3. I'm sorry, maybe I'm confused. Okay, fine.
Sure.
Planck PR3.
He asked me the question. So yeah, so we used PLIB. It's about the yeah. Your point is right. So we used in the initial paper in 2024 we used PR3, which is PLIB, plus ACT and Planck lensing. In 2025, all the results were using ComSpec, which is PR4 plus Planck lensing and ACT lensing. Yes, and this here is all based on ComSpec.
I
Yes.
have a question to clarify precisely that.
Okay.
I know that that's important.
Yes, it is. Yes,
So
it
that's
is.
the other thing that's right.
In fact, here I can even go a little bit deeper in this question. I think what we found is that between lollipop, hilipop, between PR3, PR4, and it's not, there is this A lens thing. It did not do much, but there is other paper that people where they vary this A sub L. It does have like a 0.1 or 0.2 effect on the sigma when you combine the three of them together, but not more than that. We should move on. I will finish, but yeah, please go ahead and then I will.
I'm curious about this focus on different data sets because my impression was even if you don't include like lensing corrections or whatever, right? If you just do CMB with no lensing, you will still see this anomaly at a 3 sigma level.
You will see still this
And
one,
even
yes.
if you include the prior on omega B and omega CDM from Planck without any lensing, you'll still see this anomaly.
You will see it. Lensing brings a 0.2, 0.2
So
in
that's
the
nothing.
sigma, 0.2, maybe 0.3 in some cases.
That's basically
Sigma.
nothing.
It doesn't go away. Yeah, no, absolutely not. Thank you. Your question is very clarifying. All right, let me take you again now for, here we go. So we saw some trees, okay? We saw some trees. Here is the forest, okay? So this one is a global picture of the data that I used and all the combinations. And I very much thank the TAC, the Texas Advanced Computing System, okay? Sonia knows about it. So they really were very generous into giving us time to run the jobs. And I did maybe over 50 combinations of the data sets. So this is for W naught. You see the vertical line here is the lambda CDM W naught. And this is the preference of the data here. To me, there is a message here. There is a, and then if I do again the other WA as well, so we see this, all this picture here. Someone is taking a picture, so I'm going to go back to the other one, the other one as well. So this is for W naught, and this is for WA. And now, again, the general picture, the trend, I call it the trend, the pattern, and the general picture here is, if you look at this, this is the N sigma. I plotted them all here as a function of these data combinations. I think at some time I had 50 combinations of data sets. This is maybe a little bit less. And this one is the delta chi-squares, the delta chi-squared. So, and all the data sets here, anything, any of these combinations is in support. Anything here tells you that the W not WA CDM is preferred over the lambda CDM, okay? Not even one single, and I looked for them, not even one single one tells the story otherwise. Same thing for the blue here, that the delta chi-squared. Okay, good. Let's dig a little bit more into it in the last maybe 10 minutes or so. Let's do that. If you dig a little bit down into it, you will see that it's not clear which lambda CDM is the concordance model. There is no concordance model, okay? Maybe some of you heard a little bit earlier this week about the concordance model. There is no more concordance model for lambda CDM, okay? Different data prefer different lambda CDM. It's a problem. And then this is one of my favorite slides as well. What this slide tells you is that it tells you that the story of dark energy is not a story of DESI BAO or a story of the supernovae or a story of CMB. It's a story about all the three data together. So you have if you look at this plot here, you see the vertical black line here, the vertical black line, that the lambda CDM that is preferred by Planck. If you look at the data here, this is the BAO data, and you see that this line is not the favorite. And I showed you it's in 2.3 sigma tension with this line here. Now, look at the supernovae. This orange line here is the supernovae. Same here and same here. Now, if you take the model, if we go into the supernova distance modulus, and in this one, so you see this is the dark ones here, the data point, these are from the DES year 5. This is Dovicki here. So look, the purple line here. This purple line is the line that is preferred by DESI plus the CMB. It's not the favorite for the, it's not the favorite of the supernova data set. Not for lambda, not for DES year 5, not for Dovicki, not for Union 3, not for Union 3.1 or Pantheon Plus. We don't have our Pantheon here. So the thing is that you have different data sets and you're trying to fit the lambda CDM model, it doesn't work anymore. You need something more flexible, something that W not WA does it, but maybe other models also do it. So here you see these curved line here represent the W not WA CDM models. That's why it's preferred by the data. Let's dig a little bit more into it as well. This is behind the scene now, or the consequences of that. This is W as a function of Z. We use CPL, I think you saw it at the beginning, the CPL parameterization, and this is W of Z. This is the best fit for DESI, CMB, and Union 3. Another interesting quantity to plot is the energy density of dark energy. And that's the energy density of dark energy. So interestingly, at least from what we observe here, is that in the past, it looks like dark energy here was close to its value today. Then it went up. It went up here, and then it went down closer to its value today. And you see what it means, like you can plot also Q here, and according to Q, so it's like the universe started to accelerate a little bit earlier and then gave up a little bit towards the end, the acceleration weakened. That's some part of the interpretation. Yes?
But isn't this just a feature of requiring the distance to the surface of last scattering to remain constant? It's not the data that's telling you what's happening at the very low redshift, below 0.5 or something, right? You're not measuring like Hubble or anything there.
This is today. This is today.
Yeah, I agree. But I'm saying this feature of like it going up and then having to go back down, that has to be true because you need it to be lower than the horizontal dashed line at like redshift of 1 and above. But you also want to match the distance to the surface of last scattering for the CMB. So that forces it to go back down again.
You're talking about the mirage example. There is some argument that was put in that. There are flaws in that as well.
But the omega not omega A constraint, like they don't exactly align with the mirage line, but they mostly align with the mirage line, right? There's not much, like the mirage line passes through the omega not omega A constraint. So my understanding of it is that mirage is just keeping the distance to the surface of last scattering constant, and your DESI plus CMB contours basically are like parallel to the mirage line. Maybe they're not exactly aligned with it, but they're like mostly aligned with it.
It's not, there are flaws with that mirage model compared to, I know what you are saying, that point was put forward, but this bump here is not a, this bump exists even when we do the, when we do the binning of the dark energy. So I will show you in a moment. All right, good. Some people raised their hands in the last 2 years. They say CPL is not good, and I don't like CPL. Why are you sticking with CPL? Well, we did the exercise and we looked at all the different parameterizations here. So it's not just about CPL, even all the other parameterization, they do give this behavior here. Okay, so it's not just about CPL. Now you will say the number of parameters, why are you, if you look at CPL like it's a Taylor expansion, and it's not actually. So if you look at it as a Taylor expansion, is why just 2 parameters? You could use 3, 4, 5 parameters. Kushal would have from DESI, and with DESI, we did that, and we looked at the examples of, we use Chebyshev expansion for WZ and Chebyshev expansion for the energy density. And you see that the delta chi-square, this preference, it doesn't change after 2 parameters for WZ. You see? It's more or less sticks at that value. It doesn't change. This is for the union example, okay? And then the same thing for the energy density is also more or less, it also more or less reaches a plateau. So that's the argument about the number of parameters. Furthermore, you wake up one morning and you say, I don't like functional parameterization at all for WZ. Okay, fair enough. Let's do a binning of the dark energy, the equation of state, but also binning in the energy density. And if you do the binning, okay, if you do the binning here, you see that the same behavior is observed. The same behavior is observed. And again, you see, again, it has been 2 years. We and about 2,000 papers tried all kinds of things to see whether it's due to this or to that. And again, for the binning, you change the number of parameters and you still get the same result. Now, people played, have had fun. I mean, Gaussian processes, okay? Some people tried Gaussian processes, the same result. With Gaussian processes. So I think, in my opinion, so I showed you those three slides where you see all the data combinations, and then you can exclude CMB, you can exclude BAO, you can exclude DESI, you can exclude. This is a trend. This is a pattern that we are observing. That's my message today. And what is it telling us? This is an important point. So we cannot say that this is, so we have a W0 LCDM, which is a phenomenological model. It fits the data certainly better than lambda CDM, regardless of the data combination. And now, what could it be? What could it be? There has been many papers, many proposals. I have my own ideas. There is so many things that a lot of work has been done about interacting dark energy, dark matter. Could be a sign of interactions. There has been some papers, and it could be a modified of gravity at cosmological scales, maybe more subtle, something with braiding. We did a paper on modified gravity, and we found that there is some sign of braiding into that. Thawing dark energy with spatial curvature, string theory-based models. I think the group here has a model that they are working on it, and it fits well the observations as well. Non-minimal coupled scalar field, multiple field dark energy. This is also a nice proposal by effect of inhomogeneities on the equation of state of dark energy. Perhaps they make the cosmological parameters kind of have some uncertainties from that. And then also more complex vacuum models, but certainly, or something we have no idea what it is yet, okay? Something we don't know what it is. And in my concluding remarks, so what I really was hoping very much that I have conveyed and that will be remembered from this talk is that the different different combination of data sets, they consistently favor the W0 WACDM dynamical dark energy over lambda CDM. You can set aside either supernova, CMB, or BAO, it stays. And also you can, BAO has more weight, okay? BAO has more weight into this, but you saw, I showed you a slide that even if you put DESI to the side, the result still persists. What it is, we just talked about it. It could be a bunch of interesting things. And then I would say the following, something I said 2 years ago, I said, it is tantalizing, it is exciting, we have to be cautious. We are eagerly waiting for the results from year 5 data of DESI to see, and also other experiment. Let's see what other experiment will say. But certainly these are very exciting times. Thank you for your attention.